So, welcome to lesson 10 in our study of optimization 2, where we are going to talk about the transportation problem. So, the transportation model is formulated for a class of problems with the following unique characteristics. Okay, so we consider a product being transported from a number of sources to a number of destinations at the minimum possible cost, and each source is able to supply a fixed number of units of the product, and each destination has a fixed demand for the product. So that's the scenario that we are going to consider. Okay, so although the general transportation model can be applied to a wide variety of problems, it is this particular application to the transportation of goods that is most familiar and from which the problem draws its name. So, transportation problem we mostly consider when a company produces goods at different sources, right? And after producing the goods, it has to transport them to different destinations. And each of these destinations would have a demand, and each of these sources that we produce the good will also have a supply limit. So these are the scenarios that we are going to consider. So we are going to consider a best combination which is going to transport these goods to meet supply and demand, right, at the lowest possible cost. So that's what we seek to do in transportation problems. Okay, so we are going to use this example to demonstrate the formulation of the transportation model. Okay, so wheat is harvested in the Midwest and stored in grain elevators in three different cities. So Kansas City, Omaha, and Des Moines. So these grain elevators supply three flour mills located in Chicago, St. Louis, and Cincinnati. So grain is shipped to the mills in railroad cars, each car capable of holding 1 ton of wheat, and each grain elevator is able to supply the following number of tons of wheat to the mills on a monthly basis. Right, so there's a supply. So from Kansas City, we can supply 150, Omaha 175, and the more 275. And the total supply is 600 tons. And each mill demands the following number of tons of wheat per month. Okay, so this is the demand too. So the grain elevator at Chicago demands 200. That at St. Louis demands 100, and that at Cincinnati demands 300, and the total demand is 600. So we also have to look at the cost. You see, the cost of transporting 1 ton of wheat from each grain elevator, that's the source, to each mill destination differs according to the distance and row system. So these costs are shown in the following table. So you see, we produce grain at three different places, right? Kansas City, Omaha, and Des Moines, and we want to transport it to Chicago, St. Louis, and Cincinnati. And each of these places have a demand, and each of the places that we also have the grain elevators also have a supply, right? When you are transporting it, there has to be cost. So we're now going to consider the cost. So the cost of transporting 1 ton of meal from Kansas City to Chicago is $6. That's from Kansas City to St. Louis is $8, and that of Kansas City to Cincinnati is $10. So this to that of Omaha to Chicago is $7. That of Omaha to St. Louis is $11, and it follows like that. Okay. So when we have this problem, then when we have this scenario, then the problem is to determine how many tons of wheat to transport from each grain elevator to each mill on a monthly basis to minimize. That's the most important thing here. We seek to minimize the total cost of transportation. So There's a diagram of different transportation routes with supply and demand, right? So these are the three places where we have the green elevators, right? Omaha, Des Moines, and Kansas City. So we have to transport the meal that we've produced to these three sources. So these are the ways in which we can do it. 9 different possible transportation routes, by which of them and is going to give us the minimum cost, right? And that's what we seek to address in this problem. So the linear programming model for this problem is formulated as follows, all right? So this is how we formulate it. So we are going to minimize the transportation cost, and this is how we get the transportation cost. We are going to let x, right, be a set of decision variables, right? So xij be a set of decision variables where I runs from 1 to 3 and j is a, b, c. Right, so you could see that the cost for transporting from Kansas City to Chicago is $6, and so this will give us 6s. So you see, Kansas City is 1, Chicago is a, so s1a. Then when you come here, we get x 8x1b plus 10x1c plus, when we come here, to be x2a. Right, the coefficient is 7. So that's how our objective function is going to be like. So that's why you can see that here. Minimize 6s1a plus 8x1b to 12x3c. So you should get how we formulate the objective function. Okay, then this is subject to some constraints. That's the supply and demand constraint. So this is how we get the demand constraints. Okay, so you see the demand, the supply constraint, the supply Kansas City can have is 150, that of Omaha is 175, and that of Des Moines is 275. So that means that when it comes here, right, when it comes here, Kansas City can supply a maximum of 150. So the total supply that we can have here will be 150. So that means that finding the equation for it, it will be x1a plus x1b plus x1c equals 150. When it comes to Omaha, the total supply is it 275? Yes, to 175. So that one too, we have 175 here, so it will be x2a plus x2b plus x3c equals 175. And that's how we also get for the third one. Okay, so that's how you can see that equation here. So that's the supply constraint. This. Then we also have the demand constraint. Okay, and the demand is found here. So the demand for Chicago is what? 200. That of St. Louis is 100. I think that of Cincinnati is 300. So that one, to get in the equation for it, it will be what we can see. And what we can see here is S1A. So we get S1A, and this, what we can see here is S2A. So plus S2A. What you can see here is S2, S3A, and this is equal to 200. When we come here, it will be S1B plus S2B plus S2C equals 100, and so on. So that's how we also get the constraint for the demand. That's the demand constraint, and these are non-negativity constraints. Okay, so this is the LP model for the problem, right? But don't be scared. We won't solve it in this way. There are methods that we use to solve this problem, but we are just trying to introduce you to the transportation problem. Okay, so in the above model, the decision variables xij represent the number of tons of wheat transported from each grain elevator to each mill, right? And the objective function represent the total transportation cost for each route. And each term in the objective function reflects the cost of tonnage transported for one route. And for example, if 20 tons are transported from elevator 1 to mill A, the cost $6 is multiplied by x1A, which is 20, and that will equal $120. So the first three constraints in the linear programming model represent the supply at each elevator, as I explained. And the last three constraints represent the demand at each mill. That has been explained. So as an example, consider the first supply constraint. It has been explained. So this constraint represents the tons of feed transported from Kansas City to all three mills, right? And the amount transported from Kansas City is limited to the 150 tons available. That's the supply. So note that this constraint, as well as others, is an equation rather than an inequality, because all the tons of wheat will be needed to meet the total demand of tons, right? So you could see that in this case, the total number of supply, right, is 600. The total number of demand is also 600. You can see that here. Total number of supply 600, total number of demand 600. So that's the reason when you're formulating the constraints, all of them had equal signs instead of inequality, right? So in a transportation problem where the demand is equal to the supply, we call it a balanced transportation model. So if supply exceeds demand or demand exceeds supply, then we call it unbalanced transportation model, right? And mostly to solve such models, we first have to balance it first. So realistically, however, an unbalanced problem in which supply exceeds demand or demand exceeds supply is a more likely occurrence. So in our retransportation example, for instance, if the demand at Cincinnati is increased from 300 tons to 350 tons, that means that we are adding 50 tons to the demand already, right? So that means that the total demand will be 650 and the total supply will be 600 tons. So that means that the demand is going to exceed the what supply. So as it stands now, that means when you're writing the equations for the demand, the constraint equations for the demand, you have to use less than or equal to, right? So this will result in the following change in our LP problem. So you can see that because the demand exceeds the supply, we now having less than or equal to for the demand constraints. Okay. So instead, if supply exceeds demand, then the supply constraint should rather be less than or what equal to. Okay. So note that sometimes one or more of the routes or routes in the transportation model can be prohibited. And that is, unit cannot be transported from a particular source to a particular destination. So when this situation occurs, we must make sure that the variable representing that route does not have a value in the optimal solution, right? So for instance, let's say if the sorry so if let's say the route from Kansas City to Chicago is prohibited, that means that we should make sure that when we have our optimal solution, there is not going to be any unit transported from Kansas City to Chicago, since that won't be possible. Okay, so that's what that one seeks to address. So when this situation occurs, we must make sure that the variable representing that route does not have a value in the optimal solution. And this can be accomplished by assigning a very large relative cost as a coefficient of this prohibited variable in the objective function. So for example, in our wheat shaping example, if the route from Kansas City to Chicago is prohibited, perhaps because of a rail strike, The variable x1a is given a coefficient of 100 instead of 6 in the objective function. So x1a will equal 0 in the optimal solution because of its high relative cost. Alternatively, the prohibited variable can be deleted from the model formulation. Okay, so we are still in the introduction, and I'm sure you are enjoying it. So, in a transportation problem, items are allocated from sources to destinations at a minimum cost. That's what we seek to do in transportation problem. In a linear programming model for a transportation problem has constraint for supply at each source and demand at each destination. So in a balanced transportation model in which supply equals demand, all constraints are equalities. And in an unbalanced transportation model where supply is greater than demand or demand is greater than supply, we can have equalities and inequalities, a mixture of the two. All right. So there is something brief on transportation problems. Okay, so this is what transportation problem is about, and you have to really understand what it is about before we start taking some of them and solving them. So in our next video, we will talk about method of solution for transportation problems, how to solve transportation problems. Okay, so thank you very much and see you in the next video.